Here's an example for Euler's method. I'm grabbing this particular equation and set up from a problem in your book that recommends using a computer to calculate it. So I can show you towards the end of this video how you might do that, but I want to make sure that we're okay with the general setup for Euler's method. And notice we are not given a step size in this problem, since if we had a computer we could vary it to check different approximations. The biggest thing to remember when we're doing Euler's method here is that we will need to, excuse me, let's start with make a table. So here, let me just make a table with some nice rows and columns. Hopefully I don't need any more space. So in the first column, I'm going to put my t values. Next column, my y values. And the third column, my function values, or the y prime values in this equation. I'm just going to call it f with a little n, where this is meant to indicate the function value at tn, yn. Sometimes you might see f sub n. Great. So for this particular problem, the initial point is 0 for t and 1 for y. The function value is plugging in the 0 and the 1 to the equation y prime equals t squared minus y squared. So that would be the value in the first column squared minus the value in the second column. So this would be -1. So that first row in this table will be the same no matter what value of h we pick. So for our purposes, maybe we'll pick a very simple value since we're going to do it by hand first. Let's say we had h just be a value of 1. If h is 1, then for each subsequent value of t, we add a value of h. So add 1. So t 1, 2, 3, 4, 5. Right? Now, for the values of y, that's where it gets a little bit more complicated. A good thing to remember that what we're doing in these problems is if I were to put a graph out here and just sort of imagine, well, where are we on this? Well, we're starting at the point 0, 1. So let's say it's about right there, point 0, 1. And we're asking, if I stand at this point, what direction would a solution go? This is really the same thing as you would be doing if you're looking for a direction field or a slope field. So at this point, it's going in the direction of -1. So what Euler's method says is let's go in that direction. How far? Well, we're going to go until the t value gets to 1. So where is that going to go for this particular problem? Well, to find your y value when t is equal to 1, we would say, well, we're going to start at 1 because that's where we are. And as we walk along, the y value would decrease according to this slope. So just think about how y prime is a slope, and a slope is rise over run. If you multiply that by how far you go by the run, you end up with just the rise. And so what that means is your new y value, so your y, let's write it over here, of n plus 1 is equal to where you were plus the run is h times your function value. I'm just going to write f of with a little n, sort of that notation I mentioned earlier. All right, I'm going to erase this rise over run part right here so we have some space. So for this particular problem, that tells me my next y value will be, so for this next row, where I am, I'm at 1 right now. I'm going to add h, which is 1, times f, which is -1. So that would be 1 plus -1, or 0. So we end up hitting sort of right there. Great. I'm going to zoom out just a tad here to give us a little bit more space. All right, wonderful. Then for the new function value, it's the first column squared. So 1 squared minus the second one squared. So 1 squared minus 0 squared is 1. And then we do the same thing. So for this next row, your new y value is where we are. We're at 0 now. The slope is pointing us up in a direction of a slope of 1. The step size is 1, so we have 0 plus 1 times 1. So that gives us right back up to 1. So we actually start out, end up at the same height where we began. But now at this new height, where is the direction field pointing us now? Well, at this new height, we have t squared, which is 4, minus y squared, which is 1. So 4 minus 1 is 3. So our slope now is 3. So we get a little bit steeper here, a little bit steeper. Well, let's move on. So what's the y value when we take another step going this way? Well, if the heights, or if our slope is 3, we're going to end up going up that way. So with our same formula, we're starting at 1. We're adding h times 3. So 1 plus 3 will give us 4. So it puts us up, about right here. Great, now our new slope at this point in our, again, maybe thinking like your direction field at this point where we're at 3, 4. Well, it's t squared, which is 9, minus y squared, which is 16. So 9 minus 16 is negative 7. All right, so we're going to make a big drop now. So our slope's pointing way down, way down. So where will we end up? So we're at 1, 2, 3, when your t value is 4. Well, the y value, we're at 4. We're going to add h times, h is 1, times that f value of negative 7. So 4 minus 7 is negative 3. So we actually end up coming way down below. And then this gives us a new f value. So 4 squared is 16. Minus 9 is 7. So this gives us a positive 7. So now our slope's telling us to go way back up. Well, how far back up? Well, we're at negative 3 currently, and we're going to add to that h times positive 7, so plus 7. So in this case, we go up to the value of 4. And now if we want to really make this Euler's approximation, we would connect these points with little line segments. Say, here's the approximation for this graph if we have a step size of 1. Now 1 is a little bit big, but let's sort of see how this would work out if we did it with a computer program. So I've opened up Excel here, which is a nice spreadsheet program, and I will put in my first column T, N, Y, N, and Fn, just like we did before. Now it's important to use a spreadsheet. I will need to put an equal sign when I do different equations that I want to drag, but for the first row, I just need to put the initial value. So t0, y is 1, and your function, recall, is that t value squared. So I'm going to click on it, squared, and we subtract from that the y value. Click on that y value, squared. Great. Now for the problem we just did, I had my t's always be the one above, and we added 1 to it. So I can drag that down so far. For my y's, we had it always be the y value it just was, but we're going to add to that h, which is 1, times the function value, so the direction we're going. Now I can drag each of these down, and what that does when I drag it is it takes the equation I did, and instead of referencing always, say, cell B2, when I drag it down, it will reference the cell B3, so it sort of references in a similar pattern. And there you have it. This gives us the same values that we had. So we have an approximation of value 4 for y when t is 5. Now you might wonder, is this a good approximation? Well, what we can do to check that out is we can try with different values of h. So in this case, I had added 1 each time. But what if instead of adding 1, we added something like 0.5? I need to remember to drag that down. The other thing I will need to change, I don't need to change the function because the function is just always the t cell squared minus the y cell squared. But in my calculating new values of y, there is the value of h that shows up in this equation. So what I do need to change is this value where I have a 1 needs to turn to a 0.5 to be Euler's method here. So we need to drag all these cells down. Set, find reference. All right, great. So with the value of 0.5, it gives us a 2.7 as a approximate value for y. So it's, you know, a bit different. Yeah, so 4 or 2.7 is not terribly far away, although it's not that great as well when you had the y value or the h value being 1. Just for funsies, right? Just for to see if this is a okay approximation, why don't we also try it out with 0.1 instead of 0.5? So I'm just going to change that to 0.1 and the value here to 0.1. And let's see what approximations we would get with this. I'll need to drag it down significantly further. There's 3. That was much too far. All right. So looking for the y, a t value being y. Oh, look at that. So when the t value is 5, I think I just said something very strange a second ago. When the t value is 5, the y value here is 4.9. So, you know, we actually maybe we're closer with the bigger steps. And that could happen. That could happen with these approximate methods, especially for something like this that seems to be getting a little out of control. Right? It seems to be oscillating and getting bigger and bigger. You might ask, well, what's the exact value? Well, there are ways of solving that, and that's what we'll get into as we move forward. Looking at it, it's not a separable equation, so let's maybe bring that equation back up. It's not separable. I can't write this as a function of t times a function of y, and so right now numerical methods are maybe our best. But let me show you a picture of the direction field for this, and maybe we can get another sense. Great, so I'm on a website that will graph slopes and direction fields for me. So I'm going to input our equation, t squared minus y squared, dy dt. I want the t values. I'm mostly interested in going from 0 to value of 5. And the y value, I'll see I need to make it go higher. Let's just go up from maybe, let's just do -5 to 5 and see if that gives us anything helpful. All right, great. And we're entering our initial condition. Ooh, let's clear all curves here. The initial condition of t being 0, y being 1. And it looks a little bit something like this. Oops. Sorry. Okay, great. That's when the step size was 0.1. When it was a value of, so we saw it went up to about 4.8. When it was h was a value of 1, this looks closer to what we had graphed. When the h value was 0.5, looks a little bit more like this. And you notice there's some turbulence around there. And so what you can do if you want to increase accuracy, often getting smaller step sizes is the best way of increasing accuracy for these sorts of problems. There are a few exceptions to that, but that's a good sense. There are other methods that you maybe recall. So the midpoint method, which is really the other method in our section. Let's see what it looks like here. So it gives you a little bit something different there, sort of shoots off. But there you have it. So this is just another way of getting approximate methods.